Hi, everyone. Let's review our example 1 here, where we constructed a 95% confidence interval for a population mean. So we want a CI, a confidence interval, for mu. And it's going to be centered at the sample mean x bar. All of our confidence intervals for a population mean mu will be centered about the sample mean x bar. So in example 1, we said that a machine was designed to make cartons of 16.0 fluid ounces of ice cream. So we want these kinds of cartons of ice cream. The amount of ice cream in the cartons is approximately normally distributed, which means that we can use what theorem? We can use the CLT, the central limit theorem. If the Baghdadi distribution is assumed normal, then we can use the CLT. If not, then we better rely on a large sample size. And we're going to assume that the cartons are going to have a population standard deviation of 2.35 fluid ounces. So we're assuming that sigma, the population standard deviation, is known. We're going to assume that sigma is known, which is why we're applying the methods of this lesson. Because if sigma is presumed known, then that means that we're going to use the Z table or the Z distribution. Because we want to find a confidence interval for a population mean, we're assuming sigma is known, and the CLT applies. So we're going to use a standard normal Z distribution. And then here are the sample statistics, which we're going to repeat later on. We take a random sample of 19 cartons, so little n, the sample size is 19. The sample mean, that's our value for x bar here, is 17.2 fluid ounces. And based on all of this, we found, in example 1, a 95% confidence interval for this population mean mu. Remember, the sample mean is x bar, the population mean is mu. And we wrote the CI, the confidence interval, in different forms. So when we wrote out the confidence interval, we got 17.2 fluid ounces, give or take 1.1 fluid ounces. So the population mean mu, we believe, is the sample mean, x bar, give or take this margin of error. If you work these limits out, then we can write this confidence interval in actual interval form, where we have the lower limit, where we subtract the margin of error from the sample mean. 17.2 minus 1.1 was 16.1 fluid ounces. And then the plus case, we need a plus sign here, 17.2 plus 1.1 was 18.3 fluid ounces. And again, that was our 95% confidence interval for mu. And it was centered at the sample mean. But that was for a 95% confidence interval. What if we were to construct a 99% confidence interval under the same circumstances? Would our 99% confidence interval be wider or thinner, smaller? Would it be wider or thinner or smaller? Which would it be? Well, how would the confidence interval be more likely to contain this population mean, mu? And like all confidence intervals for mu, it needs to be centered at the sample mean. Well, to be more confident that this interval will contain the true value of the population mean, we need it to be wider. We need it to be bigger. So how can we construct this 99% confidence interval? And how would this be different from the 95% confidence interval? How would the result be different? Well, it's going to be a wider confidence interval. And how will this work be different? Okay, so in example 2, we're going to look at a 99% confidence interval, CI, for this population mean mu. And again, we're going to assume that the population standard deviation, sigma, is known. This might seem like the less realistic case. I understand that. But we do get to use the z-distribution in this case. In the next lesson, we'll discuss the case where the population standard deviation is assumed unknown, which may be more realistic. Okay, so we're going to repeat example 1. It's the ice cream carton problem. But this time we're going to find a 99% confidence interval, CI, for this population mean, mu. The population mean amount of ice cream per carton. In your final interpretation, you should write this out, what mu stands for. Because if you just tell a layperson, oh, mu is between this and that, the layperson might go, what is mu? Because that is literally Greek. All right. So we're going to write the confidence interval in 2 different forms, like we did before. In this form, where the population mean is expressed as the sample mean, give or take the margin of error E, and this interval form here, where we actually work out the lower limit and the upper limit. And then we'll interpret the confidence interval. We're going to use this hint, well, these hints from the z-distribution, the standard normal distribution. Although if it came right down to it, you could figure these out using online software or tables. All right, let's do this. Let mu be the population mean, here the population mean amount of ice cream per carton. It's good to declare what mu is. The methods of this lesson apply. Again, like in example 1, why is that? Because, going up here, back in example 1, the methods of this lesson apply because we're finding a CI for a population mean mu. We're not doing a CI for sigma or P, for example. We are assuming that the population standard deviation sigma is known, which is a bit weird sounding, but we're going to run with this in this lesson. We're going to assume sigma is known. And we're going to assume that the CLT applies. We know the CLT applies here because we're assuming that the Big Daddy distribution was about normal. If you were to look at these various cartons of ice cream, we're assuming that the distribution of these ice cream amounts is normal, or about normal. So the methods of this lesson, lesson 28, they will apply. All right, same cast of characters regarding the sample statistics. The sample size n equals 19 because we sampled 19 cartons and found out how much ice cream was in these 19 cartons. The sample mean, if you take the 19 cartons, you take the amounts of ice cream, put them in an Excel worksheet, for example, or maybe a calculator. If you work out the sample mean, we get 17.2 fluid ounces. X bar. We're assuming the population standard deviation is assumed known. Sigma is 2.35 fluid ounces. Maybe this is on the label on the side of the machine. The standard deviation is 2.35 fluid ounces. And you have a 25-year warranty, a guarantee that that will not change. We're only concerned that maybe the average amount of ice cream might be changing. So a recalibration might be necessary in that sense. All right, so we have these sample statistics. The 19 may well be predetermined, actually. We have values for n, x bar, and sigma. Now you could calculate the sample standard deviation S, but in this lesson that's irrelevant. We're assuming that we know what sigma is. So we don't care if the sample standard deviation is 2.25 or 2.45. Now if it turns out the sample standard deviation is way off from this, if S turns out to be 10 fluid ounces, then you might question this assumption. Okay, we have different tests for that, finding out if sigma might be legit, this value here. All right, so the margin of error, this would be given to you on homework or exams. The margin of error, well, you can use it on homework. On a test, this would be given to you on a formula sheet. The margin of error is given by this critical value, this positive critical value from the z distribution. So for a 95% distribution, the CVs, the critical values, were at 1.96 and negative 1.96. In general, they'll be at Z sub half alpha and its opposite. Now, the hints I gave in the homework, they're consistent with these comments over here. If you're doing a 99% confidence interval and the Z distribution is involved, then you're going to want these critical values, positive 2.58 and negative 2.58. They'll be opposites. They'll be symmetric about 0. That will always be the case if we're constructing a 99% confidence interval and we want to use the Z distribution. And we're dealing with these two tails here. All right. So once again, using the hints, which I just showed you over here, we want to use these critical values, these CVs, positive 2.58 and negative 2.58. The positive 2.58 is your Z sub alpha over 2. That was that fancy notation. It represents the positive critical value. Finding my thing again. Okay, over here. In the generic notation, Z sub alpha over 2, that positive critical value. It's going to be different between a 95% confidence interval and a 99% confidence interval for Z or for any distribution. Okay, now, this is one case where our work here is going to be different from what we saw before. So how is this different? In fact, to really emphasize this, I'll put this in purple. Put a big arrow here. Whoops. I just want to circle this, the 2.58. Because for the 95% confidence interval, okay, the positive critical value was only 1.96. So we ended up with a smaller margin of error. This time, we're using a larger critical value. 2.58 is a larger positive critical value. And we have the same values for sigma and n as we did in example 1. Sigma is still 2.35, n is still 19. So if you round off the margin of error to 1 decimal place, remember we round off to the same number of decimal places as x bar was given to. X bar was given to 1 decimal place. The margin of error is about 1.4 fluid ounces. Remember that if you want to be conservative, you could round up. So if this were 1.41, we could round up to 1.5, but I'll accept either. Here, we get 1.4. Actually, let's take a look on Excel. What would we have gotten? 2.58, 2.58 times 2.35 divided by the square root of 19. Yeah, 1.39 something. That rounds up to 1.4. So whether you round off or round up, you're going to get 1.4 as your margin of error. And that's different from before. The margin of error before, in our 95% confidence interval, was bigger. It was smaller. I apologize. It was smaller, 1.1 fluid ounces. The margin of error then was smaller. The margin of error now for the 99% confidence interval is larger. It's 1.4 fluid ounces because the critical value here was larger. Okay. So to find this form of the confidence interval, we're saying the population mean is given by the sample mean, again, the 17.2 fluid ounces, give or take the margin of error, which is now 1.4 fluid ounces. It's bigger than for the 95% confidence interval. Okay, so we take the lower limit and the upper limit. We obtain these by taking the minus case and the plus case. The minus case and the plus case. From the minus case, we get 15.8 fluid ounces. From the plus case, we get 18.6 fluid ounces. So our 99% confidence interval for mu is this interval from 15.8 fluid ounces to 18.6 fluid ounces. Before, It was smaller. It was 16.1 to 18.3 because the margin of error was smaller. This interval is wider, and it's, again, centered at the 17.2 fluid ounces. The interpretation is, it's the same as before, except that we have 99% here. We are 99% confident that this interval contains the population mean amount of ice cream per carton, basically mu. But you don't want to write mu out to a layperson. We are 99% confident that this interval contains the population mean amount of ice cream per carton. So in terms of your business strategy, again, observe this is wider than what we had before. What does this analysis suggest that the ice cream company do? So you have the option of recalibrating the machine or not. And maybe it takes some money to recalibrate the machine. It probably will take some money. Will it be worth it? Well, we're trying to get 16.0 fluid ounce cartons of ice cream. The thing is, this 99% confidence interval is saying that it's quite possible that the population mean is 16.0 fluid ounces. And the fact that our sample mean was a bit high, 17.2 fluid ounces, that might be chalked up to sampling error. In fact, the 99% confidence interval is open to chalking that up to sampling error. It could be the case that the population mean for the machine is actually 16.0 fluid ounces, but this is due to sampling error. And maybe the machine doesn't have to be calibrated. This discrepancy could be due to sampling error. The cartons are supposed to contain 16.0 fluid ounces of ice cream, and the 99% confidence interval we have here for mu does contain 16.0 fluid ounces. It's between 15.8 and 18.6. Based on this analysis, the ice cream company has insufficient evidence against the claim that the population mean is 16.0 fluid ounces. So if a company rep for the machine comes by and says, don't worry about it. What you're seeing, we can chalk it up to sampling error. Your sample mean here, given your standard deviation, assuming our sigma is correct, okay, you're getting a sample mean of 17.2 fluid ounces. We can chalk that up to sampling error. Well, we, the ice cream company, okay, we have insufficient evidence against the claim, against that machine representative's claim. So we're not ready to sue them. We're not ready to recalibrate the machine. Or maybe it's not necessary. Who knows? Maybe the company might want to do it anyway just to be safe. But according to this statistical analysis, it's not imperative. It's possible that mu is in fact 16.0 fluid ounces, and what we're seeing in our sample can be chalked up to sampling error. That's possible. It's quite possible. There's insufficient evidence to suggest the need to recalibrate the machine. Again, this 99% confidence interval is wider than the 95% confidence interval. So we have greater confidence that this contains mu. However, you could say that this examination is less powerful, literally less powerful, in the sense that if the machine really does need recalibration, perhaps 99%, that's being a bit too liberal with how wide this is. 95% is the gold standard, but this is a bit subjective. What confidence level do you use? As an instructor, I'd have to give it to you, and you would work it out. It comes down to interpretation. And as for your business strategy, that may go beyond math and statistics. But hopefully, it'll be informed by statistics. Next time, let's say that you're going to conduct a study. How many people or how many cartons of ice cream do you need in order to get the kinds of results, the kind of confidence interval and precision level of confidence interval that you're looking for? Next time.